This is, in my opinion, the coolest Zig program that I've written so far. When I start learning a language, one of the things I like to do is at some point make a minimal virtual machine. I have gravitated towards Bytepusher over the years. So I'm going to pull up Bytepusher's specs and we can talk through it, and then we can walk through some of the Zig code. Bytepusher is a minimalist virtual machine invented by user Java Manon in 2010. You can think of it as a simplified chip 8 with bigger memory, bigger screen colors, and sampled sound. Bytepusher has a byte jump 1 instruction CPU. The bare bones hardware abstraction layer provides only memory mapped pixel and audio sample buffers, key states, and a fixed frame rate. All the higher level stuff, text, sprites, tiles, scrolling, sound synthesis, etc., will have to be done in software. Okay, so the features and the reason I like this, let me make this a little bigger. Bytepusher is simple. It really is simple. It takes minimalism to the extreme. A complete VM, including graphics and sound, can be written in less than 100 lines of C code. I think our Zig code is less than that. I built this in Flutter a while back, and it was significantly more. I think it was like 300 or 400 lines of Flutter code, which still is not bad for a program that can run instructions of another program. So a program that runs programs, like, not bad. It's cross-platform, so the simple structure makes it easy to write a VM for any operating system or even without an OS. It would also be simple to implement in actual hardware. Maybe we'll do that at some point too. It's persistent, so the complete machine state can be saved to a file and later reproduced exactly. We don't have anything like this in the Zig implementation or the Flutter implementation, but from a theoretical perspective, yeah, this is totally doable. Fixed size, because of the the Bytepusher memory's size, screen resolution and keyboard layout are fixed. It has a fixed speed with a fixed frame rate, CPU speed, and audio rate. It executes a fixed number of instructions per frame, which means that a Bytepusher program can't hog the host CPU. Also good. And it's 100% sandboxed. Bytepusher VM has its own fixed size sandbox memory, which it can never read or write outside of. There's some intended usage. So there are some intended uses here. Games, implementation of 2D games. I'm not really sure how reasonable that is. Maybe very small ones. It could serve as an old school platform for the demo scene. And education. Excellent tool for learning and experimentation. This is the selling point for me, but I will be very honest. It feels great when I boot up a program and pass it a file of instructions and let it just run those instructions and see it through to completion. Feels great. So the specifications, 60 frames per second, byte jump with a 3-byte address for the CPU speed, 65536 instructions per frame, so roughly 3.93 megahertz. Byte ordering is big Indian. Memories, 16 megabytes of RAM. And the graphics are 256 by 256 pixel with 1 byte per pixel with 216 fixed colors. Really nice and straightforward. If these numbers sound like a lot too, it's not that bad. And we'll get into some source code in just a moment. I know having me walk through the spec is probably not the most interesting thing. Sound, I actually don't have sound or keyboard support built into my Zig implementation yet, but the Flutter implementation has them. So I will probably follow my path with the Flutter implementation to build these in Zig probably shortly after this video is released. Might be fun for you to take my code and try to implement them as well, or maybe build it from scratch yourself and try to implement sound and keyboard support and see what that looks like. Colors. So each pixel takes up 1 byte. This would theoretically allow for a maximum of 256 different colors, but the fixed palette uses only the first 216. Indexes 216, 255 are unused, so they're set to black. The 216 colors are organized in a 6x6x6 color cube, aka the WebSafe palette. Each of the red, green, and blue components can have an intensity value from 0 to 5. The formula to calculate a pixel's color value is red times 36 plus green times 6 plus blue. You'll see this in code in just a minute. If the actual display device has 8-bit color components, we have to multiply each intensity by 33H when blitting to the screen. Keyboard layout. So this is the keyboard layout. It's the same as the chip 8. Again, I don't have keyboard support built yet, so we're going to skip over this. The memory map. This is probably... This section below is probably the most important. So you have your keyboard state here in the 0th address. In the 2 address, the program counter is fetched from that address at the beginning of each frame. Address 5, a value of ZZ means pixels, XXYY is at address ZZYYXX. In the sixth address, for 2 bytes, a value of XXYY means that the audio sample is at a certain address. Again, we don't have audio support yet, so you can ignore that part. So really all we're focusing on, this part right here and this part right here. There's an outer loop, so we wait for the next timer tick, we pull the keys and store their states. We're not going to worry about this because we are not polling supporting keyboards at this point, but we totally will at some point. Fetch the 3 program counter, or the 3 byte program counter from address 2, then execute it exactly 65,536 instructions. Send the 64 kibibyte pixel data block designated to the byte value at address 5 to the display device. Send the 256 byte sample data block to the audio device. So no audio, so we're not worried about that point yet. And then you go back to step 1. That's the program. There's an inner loop inside of this, and this is essentially those instructions. So an instruction consists of 3 big Indian 24-bit addresses, A, B, C, stored consecutively in memory. Fun fact, this part was kind of a pain to work with in Dart and Flutter. Zig made this super easy, so you'll see that too in just a minute. The operation performed is copy 1 byte from A to B, then jump to C. An instruction should be able to modify its own jump address before jumping, thus the copy operation must be completed before the jump address is read. Since the 3 address operands are limited to 24 bits, we can never copy to or from an address past a bunch of Fs and an H, and we can never jump to an instruction starting in an address greater than the same value. However, since each instruction takes up exactly 9 bytes, jumping to an address greater than or equal to this value results in the CPU attempting to read past address FFFFFH. In the worst case, if the instruction starts at FFFFFH, the CPU will try to read 8 extra bytes. The way we deal with this is to simply add 8 extra padding beyond bytes beyond that, all initialized to 0. A buggy application can then crash within the sandbox without affecting the VM or host machine in any way. This might seem trivial or like something you could skip over. This security piece here at the end is like, it's really nice. Anytime you're executing arbitrary instructions from someone else, like you should think about your application's security and reliability always, but really consider it when you're executing arbitrary instructions from someone else. Okay, so here's an implementation of the inner loop in C. So it looks something like this. We have an unsigned character, some memory address. We have that PC. I don't remember exactly what PC stands for. It's something counter, program counter. That's what it stands for. So you can see here, PC is equal to mem plus, and then we do a little bit of bit shifting to get the values that we need. Here's that number of instructions that we execute. We do those instructions until we run out of them, essentially, and the instructions are this. And that's it. The part that's really cool to me about this is like, this is so little code, but it actually does something really fascinating. And so there's some file extensions. We're just working with Bytepusher. You could essentially also support Bytepusher Page and Bytepusher Bank. For our sake, we're just working on a Bytepusher file. So here's an example. This palette test is a Bytepusher. The scrolling logo is a Bytepusher. There's a keyboard test. There's munching squares. There's an audio test that plays 8 bars of music in an endless loop while displaying a changing waveform in the style of oscilloscopes. Fascinating. There's a sign scroller, and then there's sprites and several other fun ones. The sprite one is cool. Animated fire is cool. I've got 3 of these downloaded, and we're going to execute a couple of them. Okay, so I actually don't know which file I have loaded up right now. I've just got it hard-coded into memory using the embed file built in. You could pass this as a argument or set something up where there's more UI that allows you to load files and do things like that. There's so much flexibility with this. We're going to go ahead and run this. Okay, so we have the palette test up. So the palette test looks like this. It's palettes, and that's all there is to it. There's not any keyboard interactivity in this one. Again, we don't support that in this current implementation, but yeah, something like this. Let's swap this over to a different one right quick, and then we'll execute that, and then we'll start talking through the code. Okay, we're gonna do the scrolling logo. So if I do Zig build run, things are cached. Let's let things not be cached. Zig build run. Now we have a scrolling Bytepusher logo. This one is maybe more or less interesting. There's less colors on the screen, but things are actually moving, which is pretty cool too. Okay, let's talk through the code. So I'll make this a little bigger so we can walk through it. And actually, it looks like I have more screen real estate to work with here. So let me make this a little bigger on this front as well. Okay, sweet. So we're doing a couple things. So the very first thing is we're importing the standard library. Simple enough. We're importing Raylib. So if you don't know what Raylib is a game engine rendering platform for C. There is this really great library called Raylib Zig, and it is Zig bindings for Raylib. I had not used it before. I thought it would be a great fit for this, and it turned out it was. So we'll talk about the Raylib specific pieces, but a key thing to keep in mind is in your build Zig Zon here, you will need, forgot how long this file is, access to Raylib Zig. And then in your build.zig file, there are some instructions you have to do to support Raylib here. So for example, we have Raylib GUI, Raylib artifact that we have to add here, and our Raylib dependency. And then farther down below, when we actually have our exe, we need to link the imports. So we'll use exe root module add import to Raylib and Ray GUI. Should be it. Outside of that, no other dependencies are necessary. And Raylib does support audio as well. So in theory, when we do the audio piece, we can continue to use Raylib and we don't have to use something else. As I mentioned, I'm embedding the file for the Bytepusher program. So you can download these here. So solangs.org/wiki/bytepusher. At the bottom here, there are programs. You can download programs to test things. You can write your own programs as well. Kind of fun. And so we're embedding that file. We're just getting the bytes for that file. I have a bunch of constants here. So most of these are mapped out in the spec. So we have our memory size, our key memory size, video buffer size. This is 256 pixels by 256 pixels, which is to the spec. We have screen width, which is 256, screen height, which is 256. This arguably could be a composite of these two values and probably should be. So maybe a small cleanup there. We have FPS, which is 60 frames per second. We have a color step. So that color step is also mentioned. It doesn't call it a color step, but it is mentioned somewhere in here as well. Multiplying the intensity value by 33H. So there's our color step. We have a black color that we use, so we go ahead and create that right here. And then we have our memory, which is going to be a slice of U8 of our memory size. We have our key memory size, which we're actually not using because we're not taking in keys. So this is something I started working on, and then I decided, hey, maybe I should make this video. So we'll get to that at some point, or I will get to that at some point. We have a video buffer, which is following the exact same pattern, but it's just the video buffer size, which is 256 by 256. And it's worth mentioning that I just put those all into one slice here instead of having, a slice of slices. It just seems easier to manage. So we have a color map. That color map was also mentioned. I'm going to keep referring to the docs. That color map is mentioned somewhere in here. It might not be called color map. Oh yeah, colors. Literally, we were just looking at it. So generating that color map and what that looks like. So we have Raylib colors here. We're collecting 256 of them. Here's the math to get to those colors. You can follow the instructions in the Bytepusher wiki or the SOLangs wiki for Bytepusher to see how those come to be. But the short and sweet is that it's right here. And then we're going to memset the rest of the values to color black. Then finally, we return the color slice. I have a load function here. That load function just clears out all the memory. And the reason why it does this is because Bytepusher programs can be of variable size. So if you were to just overwrite, let's say you have a program that's 100 bytes, which is way smaller than it actually will be. But for simplicity's sake, let's go with 100 bytes. And then you load in a program that's 80 bytes. The remaining 20 bytes from that first program will still exist, and it will just ruin the execution of your second program. So you need to essentially blank out all of the memory values anytime you load a new program. So we set those equal to 0 here. We get the minimum between the buffer that we pass into it, and we use that to mem copy only the relevant pieces. So whatever is smaller. So if we have a file that has a buffer that is way bigger than what it's supposed to be for whatever reason, we only copy the reasonable amount, the amount to spec that we support. And the inverse is true. So if we have a file that is under the buffer maximum, we only copy in the pieces we need. I'm going to skip past this update and draw method. We'll come back to them in just a second because I want to point out the main method. Main method's really straightforward. I call load on palette test, which is the embed file that we have up at the top. We tell Raylib to initialize a window with screen width and screen height. We give it a title. I called it Bytepusher Zig. We defer closing the window and the OpenGL context. We set our target FPS right here. This is really nice because Raylib takes care of actually making sure that we're hitting that FPS, as long as we don't do anything that would deter Raylib from being able to achieve it. And we have a while loop here. While the window should close is not true. We update and then we draw. So we'll look at those in just a second. One of the cool things that Raylib does is automatically binds the escape key unless you choose not to. So explicitly tell it not to. So if you load a program and then hit the escape key, it will terminate the program for you as well. Okay, so update and draw. So update is essentially all of the information that is covered right here. So fetching the 3-byte program counter from address 2 and execute the instructions 65,536 times. Let's take a look at that. You can see we're fetching that program counter from the address that was specified, getting it as a big Indian using standard mem read int, and then we're iterating 65,536 times. We get A, B, and C because those are the pointers that we're working with here, or the memory addresses, I should say. I guess that is what a pointer is. Feels weird calling it a pointer when it's not literal pointer, but it is a pointer in spirit. Anyways, we get A, B, and C, and then we swap them like we're supposed to. So we have memory B becomes memory A, and then the program counter becomes C. Once we execute this update function, we then call draw. Draw begins drawing, defers end drawing, so that closes out. We get some pixel addresses here following the information on colors and painting, which is right here. And then for simplicity's sake, I've got a pixel buffer here that is the full size of the video buffer. It's U8s. We grab the slice of memory that is referring to pixel addresses, and then we iterate over that and video buffer size. I get my Y and my X right here, and then I just tell Raylib to draw a pixel at those coordinates, and then the value for color is what we look up from the color map using the color index. So that's it. They mentioned a C program in less than 100 lines of code. We have a Zig program. I understand that I didn't write Raylib, and Raylib is a dependency too. But outside of that, we have 74 lines of code that is a Bytepusher emulator. And again, we are missing audio and we are missing key capture. So I have a hunch that when we add those, it'll be probably around 100, 110 lines of code. But in the meantime, 70-ish lines of code for something fun like this. So let's grab one more. I'm going to grab the sprites program. I'm going to grab downloads / what was this called? Sprites. And I'm going to move that into source. Go to line 3. We'll change this to be sprites.bytepusher. Give this a save. Let the Zig build system sort out its cache and actually save things. Come back over here, hit this with Zig build run, and then we should see our sprite program. This is one of my favorites. I can set and let you watch this for a minute. It might not be that interesting, but to me, it's very interesting. So here's what I have. Hopefully you find Bytepusher to be interesting. I love this project. It is one of my favorite projects for taking a language I'm learning and really cementing that and saying, hey, can you build a program that executes arbitrary instructions and does things and draws to the screen and eventually plays audio and supports key presses? Yeah, really, really fond of this, and hopefully you are too. I'll push up the code on GitHub. It's not up there yet, but it'll be at brad/Zig Bytepusher, Zig-Bytepusher. So that won't be in the YouTube folder. It'll be in its own because I'm going to keep working on this and maybe have some fun with it. Hopefully you found this video helpful. If you did, I would really appreciate it if you gave it a thumbs up and let me know what was helpful about it or what you would prefer to see in future videos. If you're not yet subscribed to the channel, consider subscribing so you don't miss out on more learning opportunities. We've been talking a lot about Zig lately. It'll probably continue to be Zig. That's most of what I'm writing outside of work, and I really have been enjoying it. So we'll probably continue talking about that. But we might talk about Go or Flutter or Svelte as well. I think that's it. So I'm going to sign off. Thanks, and have a wonderful day.